Here's a good review problem on fluid statics. It's from the AP Level B exam from the year 2010. This is problem number 2. And it says there's a large pan filled with some oil, and the density of the oil is rho naught. So here's our large pan, and it's filled with an oil with a density of rho naught, and it's filled to the very top. And that's with this cup sitting in it. Okay, so they tell us that the plastic cup has a mass of mc. And then with the fluid at the very top, a sample of some known mass, so that little chunk in there, ms, is dropped in, and that causes some of the oil to overflow out of the top of the pan. The oil that overflows is collected and its volume is measured, and the procedure is repeated with all different samples. So part 1, we just have to draw a free body diagram and show the forces that are acting on the system while it's floating. The system is the combination of the cup and the sample that's inside of it. So this is a really simple free body diagram. There's a force of gravity that points down. So this would be the mass of the cup plus the mass of the sample added together times g. And that's balanced out by a buoyant force that points up. The buoyant force is every bit as big as the downward force of gravity. From that, we can derive an expression and answer part B and derive an expression for the amount of overflow volume. Okay, so the buoyant force has to equal the mass of the cup plus the mass of the sample multiplied by g. But according to Archimedes' principle, buoyant force is equal to the density of the fluid, in this case that's rho naught, times g times volume. Well, the volume of the fluid is the volume that overflowed, right? So derive an expression for this volume. Oh, they call it V naught, so let's keep the same symbol they have. So all we have to do is divide both sides of the equation by rho naught g. Rho naught g all cancel out, and the volume that overflows is just equal to the mass of the cup plus the mass of the sample divided by the density of the oil. Pretty straightforward. And we've answered in terms of the variables: density of the oil, mass of the sample, mass of the cup. So as they said in the beginning here, the procedure is repeated with a variety of samples. So the data from that is collected here as the mass of the sample goes up from 0.02 kilograms to 0.03 to 0.04 and so on. The volume of overflow is recorded. So it's up to us to plot these values. So let's see, we've got to get up to a max value of 0.07. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so let's do this. Let's let every 2 lines be worth 0.01. There's 0.01, 0.02, 0.03, 0.04. If you have your own graph paper, try working along on this one. 0.06, and finally 0.07. Okay, and then we're just going to graph in units of times 10 to the negative 6 cubic meters, so we don't have to worry about the exponent. We just need to go up to a maximum of 84. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so again, let's let every 2 lines be worth 10. 10, 20, 30, 40, 50, 60, 70, 80. Yeah, get your own piece of graph paper and see if you can plot and get the same graph that I get. So for 0.02, we get 29, about there. 0.03 gives us 38 here. 0.04 and 54, that plots about there. 0.05 and 62, how about that data point? And lastly, oh no, 0.06 and 76, not quite the last one. That's that data point. And 0.07 corresponds to 84. There we go. So let's see if we can make a line of best fit. That's pretty good. Maybe we can straighten that out a little bit. Let's see. How about right there? Okay. So now we're asked to use the slope of the best fit line in order to calculate the density of the oil. Now wait a minute. I'm not sure that is a line of best fit. Let's redo that. I think I can get a better fit to the data with this line. Oops. Uh-oh. Do-over. That line seems to fit the data much better than my first line, but you notice in this case there's some y-intercept. Okay. Based on the slope of this line, can we calculate the density of the oil? Well, we should be able to. Look at the equation that we derived. This can be stated in the form V equals 1 over rho times the quantity MC plus MS, or V equals 1 over rho times mass of sample plus the mass of the cup divided by rho. And this is in the form Y equals mx plus b. After all, we're graphing the mass of the sample on the x-axis and we're graphing the volume on the y-axis, so we expect to have a slope equal to the inverse of the density. So first of all, let's find the slope. We need to pick any 2 points on our line. I like this point. And what other point seems convenient? I also like this point. So that'll give me a pretty good estimate for the slope. Rise over run. So our slope is 80 times 10 to the negative 6th minus 35 times 10 to the negative 6th divided by 0.065 minus 0.025. So we get 45 times 10 to the negative 6 cubic meters divided by 0.04 kilograms, and that's equal to the inverse of the oil density. So the oil density is equal to 0.04 divided by 45 times 10 to the negative 6th kilograms per cubic meter. You can grab a calculator and see what that comes out to. 0.04 divided by 45 times 10 to the negative 6th is equal to about 890 kilograms per cubic meter. Okay, and then the last question, what's the physical significance of the intercept? Well, again, comparing our derived expression to the equation for a line, we see there should be a y-intercept equal to the mass of the cup divided by the oil's density. So the fact that the cup wasn't massless is the reason that our best fit line doesn't hit the origin.